You wash your hands every day. Rub soap between your palms. 20 seconds, rinse, done. Simple hygiene. But what actually happens when that slippery bar meets your skin is much stranger than you ever imagined. The reason soap rips germs apart operates at a scale you cannot see and involves forces that sound like science fiction but sit in every bathroom in the world. Here is what nobody talks about. Every virus and bacterium that lands on your hand has a fatty shell, a lipid membrane. That shell is the pathogen's armor, its life support. And soap does not kill germs the way you think it kills germs. It does not poison them. It does not burn them. It tears them apart like a crowbar splitting wood, molecule by molecule. Soap physically destroys the structure that keeps these organisms intact. This is not marketing, this is chemistry. And the mechanism behind it goes back thousands of years to ancient Babylon, where someone mixed animal fat with ashes and accidentally created one of humanity's most powerful weapons against disease. But to understand why this works, you need to see what is happening at the molecular level when water and soap meet a virus on your fingertips. If you value documented scientific history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual using sources from Yale School of Medicine's March 2020. Publication on soap mechanisms and the University of York's 2022 detergent membrane research published in their news and events section, plus Professor Paul Thorderson's viral 2020 chemistry breakdown from the University of New South Wales. Now back to the information. Start with the molecule itself. A soap molecule looks like a pin. One end loves water, the other end hates it. Scientists call this amphiphilic. Hydrophilic head, hydrophobic tail. The head is charged, polar. It bonds with water molecules easily. The tail is a long chain of carbon and hydrogen, non-polar. It runs from water like oil runs from water because they do not mix. This split personality is everything. When you drop soap into water, these pin-shaped molecules do something strange. They float around as individuals for a moment. Then they start clustering. The hydrophobic tails point inward away from water. The hydrophilic heads point outward toward the water. They form tiny spheres called micelles, usually around 50 to 100 molecules per cluster, sometimes more. The exact number depends on the type of soap and the temperature of the water. These micelles are the reason soap works. They trap things. But bacteria and viruses are not just sitting there waiting to be trapped. They have their own lipid structures. Look at a bacterium under an electron microscope. Most have a cell membrane made from a phospholipid bilayer. 2 layers of fat molecules arranged tail to tail. The structure looks almost identical to a micelle, but flattened and stretched. The membrane is studded with proteins. These proteins do critical work. They import nutrients. They export waste. They communicate with other cells. Destroy the membrane and the bacterium dies. Viruses with lipid envelopes are even more vulnerable. Coronaviruses, HIV, hepatitis B, hepatitis C, herpes, Ebola, Zika, dengue, influenza, all wrapped in a fatty bilayer. The envelope protects the genetic material inside, usually RNA, sometimes DNA. The envelope also holds spike proteins. These spikes attach to host cells and punch through to inject the viral genome. No envelope equals no infection. The virus becomes inert genetic debris. Now put soap on your hands. You lather. Millions of soap molecules flood your skin. They encounter bacteria and viruses stuck in the natural oils and moisture of your epidermis. What happens next is mechanical destruction. The hydrophobic tails of the soap molecules try to escape the water. They wedge themselves into the lipid membranes of bacteria and viruses. Paul Thordarson, acting head of chemistry at the University of New South Wales, described this in March 2020. He said they act like crowbars and destabilize the whole system. The soap tails burrow into the fatty bilayer. They disrupt the weak chemical bonds holding the membrane together. The structure buckles. Here is the key detail. The bonds in a lipid membrane are not covalent. They are not strong. They are van der Waals forces and hydrophobic interactions, weak attractions. Soap molecules muscle in and break these interactions apart. The membrane starts to leak. Proteins spill out. The contents of the bacterium or virus pour into the surrounding water, dead. Or in the case of viruses, which are not technically alive, rendered completely inactive. Yale School of Medicine published this mechanism in March 2020. Essential proteins spill from the ruptured membranes into the surrounding water, killing the bacteria and rendering the viruses useless. The soap does not stop there. Some soap molecules disrupt the chemical bonds that let bacteria, viruses, and grime stick to your skin in the first place. They lift everything off the surface. Micelles form around the fragments. Picture it. A virus torn apart. Its lipid envelope shredded. Soap molecules surround the pieces. Tails inward grabbing the fatty debris. Heads outward facing the water. The micelle floats away when you rinse, down the drain with all the pathogen fragments trapped inside. That is why you need to rinse. The soap does the destroying, the water does the removing. Temperature plays a role, but not the one most people think. Warmer water increases the hydrophobic effect slightly. The soap may lather better, it may feel like it is cleaning more. But studies show that cold water and warm water are equally effective at removing pathogens when you use soap. The mechanical action of scrubbing matters more than temperature. 20 seconds of friction. That is the standard. Enough time for soap molecules to infiltrate every ridge and valley of your skin. Look at the numbers. A 2010 study had 20 volunteers contaminate their hands 480 times total with diarrhea-causing bacteria. 3 groups, no hand washing, water only. Soap and water. In the no hand washing group, bacteria were present in 44% of participants. In the water, only group 23%. In the soap and water group, just 8%. Soap and water reduced bacterial presence by 82% compared to no washing, more than half compared to water alone. During the COVID-19 pandemic, hand washing became global news. A Korean study published in July 2021 tracked hand washing behavior before and after the outbreak. Frequency increased from 6.96 times per day to 9.98 times per day. Duration increased from 20.16 seconds to 31.59 seconds. People washed longer and more often. Liquid hand soap use jumped from 23.5% to 41.3%. Hand sanitizer use exploded. But hand sanitizers are not as reliable as soap. Sanitizers with at least 60% ethanol work by destabilizing lipid membranes, similarly to soap. The alcohol molecules disrupt the structure, but sanitizers cannot easily remove microorganisms from the skin. They kill, they do not lift away. Soap does both. It destroys and it rinses. That dual action is critical. There are also pathogens that do not depend on lipid membranes. Norovirus, hepatitis A, poliovirus, rhinoviruses, adenoviruses. These viruses have protein shells instead of lipid envelopes. They are called non-enveloped viruses. Soap and alcohol are less effective at breaking them apart because there is no fatty membrane to wedge into. But vigorous scrubbing with soap still works. The mechanical action dislodges them. The soap molecules still disrupt their ability to stick to your skin. Rinse and they wash away. Not destroyed, just removed. That is enough. Bacteria like those causing meningitis, pneumonia, and certain skin infections have thick cell walls made of peptidoglycan or other structural carbohydrates. The lipid membrane is buried underneath, harder to reach. But again, soap plus scrubbing does the job. The soap lifts the bacteria off your hands, even if it cannot fully dissolve their armor. Antibacterial soap is a different story. Most contain triclosan or triclocarban. Triclosan inhibits an enzyme called enoyl acyl carrier protein reductase. This enzyme is essential for fatty acid synthesis in bacteria. Without it, the bacterial cell membrane weakens, and the bacterium cannot function. Triclosan concentrations as low as 0.3% work. That is the amount in Colgate toothpaste, according to product labels. But triclosan does not affect viruses. Viruses do not have the enzyme. They do not synthesize their own lipids. They steal lipids from host cells when replicating. So antibacterial soap marketed for COVID-19 prevention was misleading. Regular soap destroys coronavirus just as effectively because coronavirus has a lipid envelope. Triclosan adds nothing against viruses. Worse, triclosan contributes to antimicrobial resistance. Bacteria exposed to sub-lethal concentrations can adapt. Some develop efflux pumps that eject triclosan out of the cell. Others mutate the target enzyme, so triclosan no longer binds effectively. Resistance genes spread through transformation conjugation and transduction. One bacterium shares its resistance with another. Over time, resistant strains dominate. The FDA restricted triclosan use in consumer soaps in 2016 because the risks outweighed any benefit over plain soap. Go back further. Where did soap come from? Evidence from ancient Babylon dates to 2800 BC. Archaeologists excavating Babylonian sites found clay cylinders with inscriptions describing a process. Boiling fats with ashes. The ashes provided alkali, potassium carbonate. When mixed with animal fat, a chemical reaction called saponification occurred. The fat molecules triglycerides broke apart. Glycerol separated. Fatty acid salts remained. Soap. The Ebers. Papyrus from Egypt. 1550 BC describes mixing animal fats or vegetable oils with alkaline salts. Trona, a natural mineral. The Egyptians used this substance for personal hygiene and in mummification. The Greeks favored olive oil mixed with lye. The Romans initially avoided soap. They preferred the strigil method. Rub oil on your skin, scrape it off with a curved metal tool, take the dirt with it. But by 58 BC, the Romans started using Gaulish soap made from tallow and ashes. Pliny the Elder in the 1st century AD credited the Gauls with inventing soap. Germanic tribes used it medicinally and as a hair dye. By the 2nd century AD, the Greek physician Galen promoted soap for personal hygiene. He noted the best quality came from the Germanic regions. Soap making expanded during the Islamic Golden Age from the 8th to 13th century AD. Arab chemists refined the process. They mixed fatty oils with alkali and added pleasant scents. Cities like Aleppo, Damascus, and Nablus became major soap exporters. In Europe, soap production spread to Naples by the 6th century AD. By the 8th century, it was common in Italy and Spain. Medieval Europe saw large-scale soap manufacturing in Marseille, Castile, Antwerp, Venice, and Genoa. Olive oil replaced animal fats in Mediterranean regions. The soap became milder, less odor, better for skin. Soap remained expensive for centuries. Monopolies controlled production. The price dropped significantly in 1791 when French chemist Nicolas Leblanc discovered a method to synthesize sodium hydroxide from salt, man-made lye. Cheap lye meant cheap soap. 20 years later, another French chemist, Michel Chevreul, identified the relationship between glycerin fats and fatty acids. That discovery marked the beginning of modern soap chemistry. By the 1800s, soap became affordable for the general population. Today, soap is everywhere. Bars, liquids, foams, gels. The base mechanism remains identical to Babylonian soap from 5,000 years ago. Fatty acids plus alkali equals soap. Amphiphilic molecules. One end loves water, one end hates it. Simple, effective, universal. Now consider what happens inside your skin. The outermost layer of your epidermis is the stratum corneum. Around 15 layers of dead flattened cells. These cells lost their lipid membranes when they died. They have protein shells called cornified envelopes instead. Tough, structural, keratin heavy. Soap does not damage these cells much because there is no lipid membrane to wedge into. You shed millions of skin cells daily anyway. Losing a few extra to soap is harmless. But bacteria and viruses are single-cell organisms. Bacteria have one cell. Viruses are not even cells. Just genetic material in a lipid wrapper. One dose of soap and they are gone. Your skin regenerates, they do not. Here is another angle. Soap molecules can be visualized under the right conditions. Scientists use fluorescence microscopy to track how detergent molecules interact with membranes. A 2022 study from the University of York used single-molecule FRET, fluorescence resonance energy transfer. They created artificial membrane balls. Then they added tween-20, a common detergent. They measured how the membrane components moved apart. The results showed that tween-20 binds to the membrane. The balls expand. Pores form on the surface. Then the membrane fragments completely. The researchers confirmed this with computer simulations, molecular dynamics models. The simulations match the experimental results. The detergent molecules penetrate the bilayer. Mechanical stress builds. The membrane cannot hold, it ruptures. This is the same mechanism for soap. The hydrophobic tails insert, strain increases, the bilayer breaks. Micelles form around the fragments. Rinse, gone. Another study in 2021 from Yale found that human cells produce a protein called apol-3 that acts like soap inside the body. A polypoprotein L3. It has both water-loving and lipid-loving parts. When bacteria like Salmonella invade cells, apol-3 binds to the bacterial inner membrane. It dissolves the membrane into the intracellular fluid, like soap washing away grease. The bacterium dies. APOL3 works with another protein, GBP1, guanylate binding protein 1. GBP1 loosens the bacterial outer membrane. APOL3 then targets the inner lipid membrane. Together, they kill the invader. The human body essentially makes its own detergent to fight infection. This discovery, published in Science in July 2021, shows that soap-like molecules are part of ancient immune defenses, not just external hygiene, internal warfare. The hydrophobic effect drives all of this. Water molecules are polar. They form hydrogen bonds with each other. When a nonpolar molecule, like a lipid tail, enters water, the water molecules rearrange. They form a cage around the nonpolar intruder. This decreases entropy. The system does not like it. The water wants to maximize disorder. So nonpolar molecules get pushed together. They aggregate, minimize contact with water. Oil droplets form, lipid bilayers form, micelles form, all driven by water trying to stay disordered. Soap exploits this. The hydrophobic tails cluster with other hydrophobic substances, lipid membranes, grease, oil, dirt. The hydrophilic heads interact with water. The result is a bridge. The soap pulls the hydrophobic grime into the water by wrapping it in a water-friendly shell. The micelle. The grime gets solubilized, washed away. Temperature affects micelle formation through something called the Kraft temperature. Below this temperature, surfactants stay as crystals. They do not dissolve well. They do not form micelles spontaneously. Above the craft temperature, they dissolve and assemble into micelles easily. For most hand soaps, the craft temperature is well below room temperature, so even cold water works. But raising the temperature slightly can increase the rate of micelle formation. Faster lathering, more micelles, potentially more effective cleaning. Critical micelle concentration is another factor. CMC. This is the minimum concentration of a soap needed for micelles to form. Below the CMC, soap molecules float individually. Above the CMC, they aggregate into micelles. More soap means more micelles, but there is a limit. After a certain concentration, adding more soap does not increase cleaning power. You hit saturation. Ethanol in hand sanitizers works differently. Alcohol denatures proteins. The spike proteins on virus surfaces unfold. The structure collapses. Ethanol also disrupts lipid membranes, but through a different mechanism. It does not wedge in like soap. It shakes everything apart. A molecular earthquake, the membrane fragments. The virus or bacterium falls apart. Combining ethanol and soap creates a powerful team. Soap wedges into membranes. Ethanol denatures proteins. Together, they tackle a wider range of pathogens. Some antibacterial formulations contain both. Essentially, hand sanitizer plus soap. Marketed as antibacterial soap, but really just a hybrid product. During the COVID-19 pandemic, Professor Paul Thordarson became famous for a Twitter thread in March 2020 explaining how soap destroys coronavirus. He described SARS-CoV-2 as a self-assembled nanoparticle. The weakest link is the lipid bilayer. Soap targets that weakness. The thread went viral, millions of views. Thordarson had studied lipids for years, nanomedicine, supramolecular chemistry. But he never expected a Twitter thread to reach so many people. His explanation was simple. The coronavirus is a greasy little meat particle. The lipid tails on soap molecules avoid water by sticking into the greasy virus. The soap pries the virus apart like a crowbar. The virus disintegrates. Thordarson compared it to mixing oil and water with soap. The soap surrounds the oil, breaks it up, disperses it. The same happens to the virus. One study during the pandemic tracked hand washing compliance in healthcare settings. Before COVID, 19 compliance was around 40%, shockingly low. In critical care units, it was 46.25%. Simple, life-saving, still neglected. The pandemic changed that temporarily. Compliance increased, media campaigns, public health messaging. Hand washing became front-page news. But a study from 10 African countries showed something troubling. In July 2020, hand washing rates were high. By November 2020, they had declined significantly, despite rising COVID cases and deaths. Why? Possibly because other behaviors like mask wearing and distancing took priority. Health messages emphasized masks. Hand washing got less attention. Or maybe people grew tired. Pandemic fatigue. The initial urgency faded. A systematic review of hand washing effectiveness against respiratory viruses found a 45 to 55% reduction in transmission with proper hand washing. Another review, focused on H1N1 influenza, found a 38% reduction. Hand washing worked consistently across multiple studies, yet access remains unequal. A 2020 study estimated global access to hand washing facilities. 3 out of 5 people worldwide have basic hand washing with soap and water at home. 40% of the global population, 3 billion people, lack this access. In least developed countries, nearly 3/4 lack basic hand washing facilities. 47% of schools worldwide have no hand washing facility with water and soap. That affects 900 million school-aged children. 16% of healthcare facilities lack hand hygiene services. 1 in 6. No soap, no water. At the point of care, urban populations face high risk during pandemics due to density, crowded markets, public transport, places of worship. Yet cities like Addis Ababa, Nairobi, and parts of Delhi have low hand washing access. 58% in Addis Ababa, 54% in Nairobi. 15% in urban Delhi lack hand washing facilities. Social distancing is hard. Hand washing is harder when there is no water or soap. Alcohol-based hand rubs offer an alternative. 60% ethanol or higher. Effective, portable, but they do not remove dirt. They kill pathogens on contact. If your hands are visibly soiled, hand rubs are less effective. You need soap and water, mechanical removal, soap lifts, alcohol kills. Different tools, both necessary. Bar soap versus liquid soap. Does it matter? Some worried during the pandemic that bar soap could harbor bacteria. It is true that bacteria and viruses can transfer onto bar soap during use. Studies found bacteria on bar soap surfaces, but washing with that soap still leaves your hands clean. The lather washes away the pathogens. Rinsing removes them. Bacteria do not survive well on dry soap anyway. Between uses, the soap dries. Most pathogens die. Bar soap is safe. Liquid soap is more convenient in public settings. Pump dispensers are touchless, less cross-contamination. But at home, bar soap works just as well. The key is proper technique. Wet hands, apply soap, and lather for at least 20 seconds. All surfaces, between fingers, under nails, backs of hands, rinse thoroughly. Dry with a clean towel or air dry. Hand drying matters too. Wet hands pick up pathogens more easily than dry hands. Paper towels are ideal. They absorb water and remove remaining microbes through friction. Electric air dryers work but take longer. In low resource settings, clean towels or even drying hands on clothing is better than leaving them wet. A study in Zimbabwe found that drying hands on clean towels or even dirty clothes removed more bacteria than air drying. Soap is cheap, dirt cheap. It does not harm us. It does not harm the environment significantly. It breaks down quickly. Biodegradable. No better alternative exists. Thordarson said it. Soap is as good as it gets for everyday hygiene. 5,000 years of use. Still unbeaten. Now the mechanism at the nanoscale. Imagine a virus particle, roughly 100 nanometers across, a sphere of lipid bilayer, spike proteins jutting out, inside RNA strands and nucleoproteins. The virus lands on your hand, sticks to skin oils, stable, infectious. You apply soap. Millions of molecules swarm the virus. Hydrophobic tails probe the lipid envelope. They find weak spots, insertion points. The tails burrow in, more and more. The bilayer distorts, curvature increases, mechanical strain builds. The proteins in the membrane lose their anchors. They drift. The bilayer thins. A pore forms, small at first, then larger. The contents leak. RNA spills into the water. The envelope shreds. Soap molecules surround the fragments. Micelles engulf the debris. Rinse. The virus is gone. Not mutated, not resistant. Physically dismantled. This is not chemical warfare. This is mechanical demolition. The soap does not need to evolve. The virus cannot adapt. The lipid bilayer is not something the virus can change. It is structural, fundamental. Without it, the virus cannot exist. So soap remains effective. No resistance develops, no arms race, just physics and chemistry working every time. Compare that to antibiotics. Bacteria evolve resistance by mutating target enzymes or acquiring efflux pumps. Antibiotics lose effectiveness. New drugs are needed. Constant cycle. But soap has worked for 5,000 years. It will work for 5,000 more. The laws of chemistry do not change. One more detail. Soap molecules self-assemble. You do not need heat. You do not need pressure. You do not need catalysts. Just mix the ingredients. Fats and alkali. The reaction happens. The molecules organize themselves. Amphiphilic structure emerges automatically. Nature favors this arrangement. It minimizes free energy. The system settles into the lowest energy state. Micelles form. Bilayers form. Self-assembly. This is why soap is so universal. Any culture with access to fats and ashes can make it. Babylonians did, Egyptians did, Gauls did, Romans did, Chinese did using plant materials. Every civilization figured it out independently. The chemistry is intuitive. Even without understanding the mechanism, ancient peoples saw that this mixture cleaned. It removed grime. It felt different on skin, so they used it, refined it, traded it. By the Middle Ages, soap was an industry. Guilds formed, trade secrets emerged. Different regions developed signature soaps. Castile soap from Spain, Marseille soap from France, Aleppo soap from Syria, each with unique ingredients. Olive oil, laurel oil, goat tallow. Different fats produced different textures and scents. But the core mechanism remained the same. Amphiphilic molecules, hydrophilic heads, hydrophobic tails, micelle formation. Membrane disruption. The word soap comes from the Latin sapo. First appeared in Pliny the Elder's Historia Naturalis. Legend says soap got its name from Mount Sapo in Rome, where animal sacrifices occurred. Fat and ashes ran downhill into the Tiber River. Women washing clothes in the river noticed the water cleaned better there. The legend is probably false, but it captures the accidental nature of soap's discovery. Someone somewhere noticed that mixing fat and ash with water produced a cleaning agent. The observation spread. The practice became universal. Saponification is the chemical process. A triglyceride fat molecule has 3 fatty acid chains attached to a glycerol backbone. Add sodium hydroxide or potassium hydroxide. Lye. The base breaks the ester bonds. The glycerol separates. The fatty acids bond with sodium or potassium ions. You get soap. Sodium soaps are hard. Potassium soaps are soft or liquid. The type of alkali determines the texture. Modern soap making uses the cold process or hot process. Cold process mixes oils with lye at room temperature. The mixture heats up from the exothermic reaction. You pour it into molds. Wait days for saponification to complete. Curing takes weeks. The soap hardens. Excess water evaporates. Hot process speeds this up. Heat the mixture while stirring. Saponification happens faster. You can use the soap sooner. Both methods produce the same end product, amphiphilic molecules. Superfatted soap contains extra oils. Not all the fat reacts with lye. Leftover oils moisturize skin. The soap feels gentler, less drying. Some soap makers add glycerin back in after separating it. Glycerin is a humectant. It attracts moisture. Glycerin soap feels smoother, more luxurious. But the cleaning power comes from the soap molecules themselves, the amphiphilic structure. Everything else is cosmetic, fragrance, color, texture, marketing, Thordarson called it. The entire soap industry is 99% marketing. All soap works the same way. Expensive artisan soap, cheap bar soap, liquid hand soap, same mechanism, same molecules, same results. The difference is branding, scent, packaging, feel. But the core function, destroying lipid membranes and forming micelles, is identical across all products. pH matters slightly. Soap is alkaline, usually pH 9 to 10. Your skin is slightly acidic, pH 4.5 to 5.5. The alkaline soap temporarily raises your skin's pH. This can feel drying. Your skin produces sebum to restore the acid mantle within hours. Frequent washing can disrupt this balance. That is why dermatologists recommend moisturizing after washing, especially in people with eczema or sensitive skin. But the alkalinity does not affect soap's ability to destroy germs. It is the amphiphilic structure that matters. Some soaps contain chelating agents, EDTA, ethylene diamine tetraacetic acid. Chelators bind metal ions, calcium, magnesium. Hard water contains these ions. They react with soap to form soap scum. The white residue in your sink, chelators prevent this. They keep the soap effective in hard water. But again, this is a convenience feature, not a germ-killing feature. Preservatives in liquid soaps prevent microbial growth in the bottle. Parabens, phenoxyethanol, sodium benzoate. These stop bacteria and mold from colonizing the soap itself, but they do not add to the soap's effectiveness against germs on your hands. The base soap molecules do that work. One study tested soap effectiveness in contaminated water. Even if you wash with highly contaminated water using soap, your hands still come out clean. The soap molecules remove pathogens, regardless of water quality. Obviously, clean water is better. But in low-resource settings where water is not pristine, soap still works. This is critical information for public health interventions. You do not need drinking quality water for hand washing. Any water plus soap equals clean hands. Tippy taps became popular during the pandemic. Simple hand washing stations, a container with a small hole, tilt it, water flows. Foot pedal or string operated, touchless. You can set them up anywhere. Markets, roadsides, rural areas. Cheap to build, effective. The challenge is keeping them supplied. Water and soap need regular replenishment. But the concept works. Low tech, high impact. Public hand washing campaigns saved lives during COVID-19. Billboards, radio spots, social media. Everyone repeated the same message. Wash your hands, 20 seconds. Soap and water. The campaigns worked. Hand washing rates increased globally. In South Korea, frequency jumped by 43%. Duration increased by 57%. People took it seriously, at least initially. But maintaining behavior change is hard. Fatigue sets in. Other priorities emerge. The decline in hand washing rates by late 2020 shows how quickly habits slip. Public health messaging must be sustained, repeated, reinforced, not just during crises, always. Schools are critical. Teaching children proper hand washing establishes lifelong habits. Yet half of schools in least developed countries have no hand washing facilities. This is a solvable problem. Simple infrastructure, soap dispensers, water access. The cost is minimal. The return is enormous. Reduced disease transmission, fewer school absences, better health outcomes. Healthcare facilities without hand hygiene are unacceptable. 16% globally in settings where infections spread easily, where vulnerable patients are concentrated, no soap, no water. This is not just a hygiene failure. It is a fundamental breakdown in care. Investing in hand washing infrastructure in clinics and hospitals should be a global priority. One more scientific detail. Recent research explores how soap molecules interact with different types of lipids. Phosphatidylcholine, phosphatidylethanolamine, sphingomyelin, cholesterol. Membranes contain mixtures of these. The ratio affects how easily soap disrupts them. Membranes rich in cholesterol are tougher. Cholesterol stabilizes the bilayer, makes it more rigid. Soap takes longer to break it apart, but it still works. Just requires more time and scrubbing. Bacterial membranes have less cholesterol than mammalian membranes. Human cells have lots of cholesterol. This is why soap does not harm your skin cells as much. The cholesterol protects them. The outer dead cell layer has no membrane at all, just protein shells, so soap cannot damage it. But bacteria with low cholesterol membranes are vulnerable. Soap rips through them. The protein APOL3 mentioned earlier targets lipids specific to bacteria. It avoids cholesterol-rich membranes, so it kills bacteria inside human cells without harming the human cell itself. Selective targeting. This is a form of innate immunity. Soap inside cells, evolutionary pressure led to this. Organisms that could make soap-like molecules to fight infections survived better. The trait persisted. Now it is part of our immune system. This suggests that the soap mechanism is ancient, not just 5,000 years, millions of years. Evolution discovered it. Cells use it, we just externalized it. Took the same molecular strategy and applied it outside the body. Hand washing is not a modern invention. It is an ancient defense scaled up. Think about that. Every time you wash your hands, you are using a molecular weapon that evolution refined over eons. The same forces that protect cells from bacterial invaders, the same chemistry that keeps membranes intact or tears them apart depending on the molecule. You are harnessing billions of years of natural selection every time you lather up. Now the final detail. In 2022, researchers used advanced imaging to watch detergent molecules in real time. They tagged the molecules with fluorescent markers, watched them bind to artificial membranes, measured the expansion, tracked pore formation, recorded fragmentation. The entire process took seconds to minutes depending on detergent concentration. They used Tween 20, a common lab detergent, similar to soap. The results showed that after binding, the membrane balls expanded significantly. Surface area increased by up to 50%, then pores appeared. Small holes, they grew, merged. The membrane became Swiss cheese, then it shattered. Fragments floated away. The whole structure collapsed. Molecular dynamics simulations confirmed this. Computers modeled millions of atoms, calculated forces, predicted movements. The simulations matched the experiments perfectly. Detergent molecules insert into the bilayer. They create mechanical stress. The membrane cannot withstand it. It breaks. This is physics, not biology, not chemistry in the traditional sense. Mechanical force. The soap molecules do not react chemically with the lipids. They just push, wedge, pry. The bilayer yields. Structure fails. Game over. This is why soap works on so many pathogens. It does not target a specific protein or enzyme. It targets the structure itself. The lipid bilayer. Any organism or virus that uses a lipid envelope is vulnerable. No exceptions, no resistance, no escape. One study in 2010 measured bacterial removal. Volunteers washed hands. Researchers swabbed before and after. Counted colonies. Soap and water reduced bacteria by 80 to 90%. Water alone reduced by about 50%. Soap doubled the effectiveness. The mechanical action of scrubbing plus the chemical action of soap. Together, they work. Compare that to hand sanitizer. Alcohol kills 99.9% of bacteria in lab tests, but in real-world conditions on actual hands, it is less effective. Around 90 to 95% reduction. Still good, but not as thorough as soap and water. Why? Because alcohol does not remove. It kills in place. Dead bacteria stay on your hands. Soap removes them, washes them away. Physical extraction. This matters for non-enveloped viruses. Norovirus, for example. Alcohol does not destroy it well. The protein shell resists, but soap and scrubbing dislodge it. Mechanical removal. Rinse it down the drain. The virus does not need to be destroyed. It just needs to be gone. Soap achieves that. During norovirus outbreaks, hand-washing compliance is critical. Alcohol sanitizers fail. Only soap and water work reliably. Public health agencies emphasize this. Norovirus causes gastroenteritis, vomiting, diarrhea, highly contagious, cruise ships, schools, nursing homes. Anywhere people congregate, proper hand washing stops transmission, nothing else does. The same applies to other non-enveloped viruses. Adenovirus, rotavirus, poliovirus, soap and water, scrub, rinse, repeat. Simple, effective, irreplaceable. One final study worth mentioning. Researchers tested how long soap needs to be on hands. They found that 10 seconds is insufficient. 15 seconds is better, 20 seconds is optimal. Beyond 20 seconds, there is minimal additional benefit. The plateau happens because most accessible pathogens are removed by 20 seconds. Anything left is deeply embedded in skin folds or under nails. Even vigorous scrubbing for a full minute does not remove everything. But 20 seconds removes enough. Risk drops to acceptable levels. The 20-second rule is not arbitrary. It is based on evidence, time studies, pathogen counts, risk analysis. Public health agencies worldwide converged on this number. CDC, WHO, National Health Ministries. I'll say 20. It works. Sing happy birthday twice. That is roughly 20 seconds. Count to 20 slowly. Use a timer. Whatever works. Just make sure you hit 20. Anything less leaves too many pathogens behind. Now the end. A discovery that changes how you see soap. In 2023, researchers excavated a soap workshop in Pompeii. The site had been debated for years. Was it a soap factory? Some thought it was a laundry, others a fullery, a place for cleaning wool. New analysis confirmed it. Soap production. The workshop had large vats. Residue tested positive for fatty acids and alkali. Finished bars were found, rectangular, stamped with maker's marks, identical to modern soap shapes. Pompeii was destroyed in 79 AD. This workshop was making soap almost 2,000 years ago, using the same process we use today, the same chemistry, the same product, frozen in time by volcanic ash. Those bars sit in a museum now. You can see them. Touch them. They look like soap. Because they are soap. Molecular structure unchanged. Amphiphilic molecules. Hydrophilic heads. Hydrophobic tails. Ready to destroy any lipid membrane they encounter. 2,000 years later. COVID-19 pandemic. Global crisis. The solution? Soap. The same mechanism. Ancient technology. Modern salvation. Soap does not change. It does not need to. The laws of chemistry are fixed. The structure of lipid membranes is fixed. Soap exploits that. Forever. Reliably. Universally. You wash your hands. Soap molecules swarm. Hydrophobic tails wedge into lipid envelopes. Mechanical stress builds. Membranes rupture. Proteins spill. Viruses shred. Bacteria die. Micelles form. Rinse. Gone. Simple chemistry. Devastating effectiveness. 5,000 years proven. Billions of lives saved. And you hold it in your hands every single day.